Okay, real quick, to do these, the first thing you'd have to do is draw what's called electron dot notation. And electron dot notation is just showing all the valence electrons around the outermost shell of a particular element. And the most you can have around any shell of an element is 8. When you count across the periodic table, starting with group 1, that'll have 1 dot or 1 valence electron around it. So if we did sodium, for example,
What's this called?
electron dot notation.
Oh, okay.
Okay? If we show sodium, it would just be 1 dot. Okay? Group 1. It's 1s. For example, sodium would be it'd be neon, and it'd be 3s1. Okay? Potassium, it would be argon and 4s1. So it's the S1, the P values in that shell. So again, this shouldn't take us too long. Sulfur, how many electrons does it have? Its outermost shell. And you just look at the outer S and P. 6. And it doesn't really matter for us how you originate and show those 6 electrons, but that's what maybe you could show it as. Okay? And if you notice when you get to the very end, neon, for example, it has 8. And we call that an octet of electrons. Okay? So it has an octet of electrons. What we're going to do is we're going to show structures to begin with that obey the octet rule. We're also going to expand that to structures that don't have to obey the octet rule. Okay? And show you a method that works for every one of them. So this method of going through the steps, working through these step by step, will help you with doing all of them. Not just one, but all of them. Okay? What's that? Yeah, if you got your handbook, that would be helpful. She requires that for us to do that. Okay, let me real quick get our objective up here. Yeah, go ahead. There you go. Thank you. All right. Again, we're going through this really quick. All right? So, first thing we'll do is we'll write these structures out that obey the octet rule. He's not here today.
Not here today. Okay.
Yes, he's gone. And to do that, we'll do some steps, and you guys can write these down, or you don't have to. If you feel the steps have to be reviewed from time to time to help you, I would encourage you to do so. All right? First step, okay, in writing Lewis structures, is to count the total number of valence electrons in the compound. Okay, we'll start out really simple when we do this. So here's our structure.
What did it say?
I'll go back. So here's our structure. Write that down. You might want to leave half the page and go down so that as you're writing this out, we can use the steps as we go through one of these examples. Okay? So, again, add up the total number of valence electrons in the structure. Okay? So do that. Find carbon, count how many valence electrons it has. Find hydrogen, count those total. And then go ahead and find the iodine and count all those up and add them all up. Okay? So, Ci2H2. What it is. So you're going to take carbon, count them.
Like the dot notation thing?
Yep.
Okay.
You don't have to draw them out. If you can count across, you don't have to draw it out every time.
Right, okay.
Because that just takes time to do, and all you're basically doing is counting and writing them down and adding, you can add them up in your head. Okay? So how many do we have? How many valence electrons? 20. You're not going to end up with an odd number. So when you do these, you're not going to end up with odd numbers. They're always going to be paired up. So electrons are always paired up, whether they're shared pairs or unshared pairs. Okay? Second thing that you're going to do is you're going to determine which element should be your center element. Okay? So there's always a center element on these structures that will be surrounded by what we call branched atoms. So determine the central atom by counting the number of electrons that it would have. And the atom with the fewest electrons surrounding it is their central atom. Okay? Alright, there's one exception though. This atom never goes in the middle. Which one does never goes in the middle even though it has the fewest?
Hydrogen.
Hydrogen. Exception is hydrogen. Okay? So, go ahead and do that with the example that I just gave you. The one that is central has the fewest number of electrons. Write that symbol in the middle and then surround it by the other symbols. Does not have to be in any particular form as long as you have those four around the central atom. And it doesn't matter where they're going to go. Because as we know with something that's three-dimensional, you can rotate it and move it around so that it would have a certain particular arrangement. So we can't do that with the two-dimensional, especially on paper. So it really doesn't matter how you have those originated with one another. Okay? Right. The third step that you would have to do would be show at least one shared pair between the central atom and the branched atom. For each branched atom, you will show one shared pair between the branched atom and the central atom. Okay? Now, that original 20, we're going to have to keep track of it because we can only show 20 electrons or 10 pairs of electrons when we are done. So we need to keep that in mind, that number of 20, as we go through and do these. So I'm just going to, in my head, I'm going to take away 8, and I'm left with 12 electrons, right?
Wait, because you put 2. Just keep going.
Yep, they're just pairs. So between each one, you have a pair of electrons.
But I thought hydrogen only had 1 for each one.
Hydrogen can have 2 with it.
Oh, it can.
Yep. Now, hydrogen is in the first shell, and it can only have 2. So, this next statement hydrogen's finished. When we draw these structures out, hydrogen is finished once you share a pair between it and the central atom. It is done. It is maxed out. It has its full shell. Hydrogen is an exception on a lot of these that we do because it can't have 8. Okay? It has 2 to have a full shell. Alright? Number 4, what you're going to do is make sure all the branched atoms have 8 electrons by putting 6 electrons or 3 pairs of electrons around each branched atom. Okay, so in addition to the shared pair, you're going to add additional 3 pairs of electrons to each of the branched atoms. Okay? So, again, hydrogen we don't do. So we're going to put our unshared pairs, that's what they call these, that are not sequenced between 2 different atoms. So once we do that, we count up how many we use to get those all filled in, and we're to 0 electrons. So we are finished with our structure. Now, one here we're going to do here in a second will not complete an octet of electrons. So we want to make sure everything in these examples I'm going to show you now has at least 8 electrons around it. Okay? It has to have at least 8. If it doesn't have at least 8, then it doesn't follow the octet rule. And for right now, we're just doing those ones that finish the octet rule. Another way to draw this that helps is to use lines for every pair between the central atom and its branched atoms. So this is another way to show this without showing all those dots. So we can show it that way. And that's a tetrahedral structure. Now, we're not going to go shapes today, but we'll do it tomorrow. But that's a tetrahedral structure with single bonds. Okay? Now we're going to add one step to make sure that we're fulfilling the octet rule, and then we'll start getting multiple bonds now. Okay, so this is all review, stuff that we've done. I'm going to have you do the first 3 steps, or 4 steps, of this next one. And you'll find out the central atom will be lacking 8 electrons around it when you're done. So, I want you to do an example like this. And go through the steps, 1 through 4, stop, and then see if you can remember what we did to allow the central atom to get 8. Okay?